actually.
Okay. It's not working. Yeah. Hello, everyone. In the morning, I talked about the basic concepts of chemical kinetics, the various definitions and numerical expressions. Out of that, very important numerical expressions we will take, and which will be sure for the examinations, and try to remember that. And also, we would like to throw light upon how this graphical representation and numerical expressions are related, right? So numerical expressions, so which are very importantly coming are one is integrated rate expressions. One which is definitely coming, one are integrated rate expressions. Okay. Integrated rate expressions are different for different ordered reaction. For zero order, recall with me which are the one which you have to take is rate, or rate is equal to rate constant. Here rate is equal to rate constant, and rate constant is equal to concentration of initial concentration, final concentration divided by T. This is the expression for rate or rate constant. Both are equal in the for the zero order reaction. And T half. What is meant by T half? It is the half-life period. Half-life period, final concentration becomes half of it. Therefore, this is R0 minus R0 by half, that is R0 by 2. R0 by 2, this is okay, K, 2K. So this is expression for zero order reaction. For the first order reaction, we have rate constant K is equal to 2.303 divided by T log to the base 10 concentration of R naught by concentration of R naught by R, initial concentration by final concentration, right? And T half is equal to 0.693 by K. So these are the mathematical expressions, okay? And initially we defined rate, okay, we can write here. Rate is equal to K into, if A and B are the two reactants, can you able to see that? Okay, it's not possible. I leave this place. Okay. These are the mathematical expressions which are very important. What way the questions are asked is how long it will take for the initial concentration to take its value 1/16th value. Initial concentration is not known. Initial concentration will be changed into 1/16th of its value. How much time is taken for that? You may ask to find out this. So rate constant K value will be given, and you have to find out how long it takes. T value you have to find out. So T to be taken here, K will be here. And R naught by R, that is the decision. R naught by R is, if suppose that is X, initial concentration is X, then 1 by 16th of X is the final concentration. Therefore, X and X get cancelled, and 1 divided by 1 by 16 is log of 16. Okay. So remember these values which are oftenly required to be remembered. Log of 2 is equal to 0.3010. Remember this value, log of 2, 0.3010. Oftenly in the multiples of, in the exponents of 2 only it will be asked. So 8 can be written as 2 to the power 3. Log of 2 to the power 3 is 3 log of 2. Therefore, you need not refer the log table. Okay. In this way, it helps you. Therefore, remember the log 2 value, 0.3010. Okay. Textbook questions are mainly to be done because many a times textbook questions are directly asked in this regard. Now, another expression about that I was talking about. This is the Arrhenius equation. Arrhenius equation, K is related to frequency factor, and this is minus EA divided by RT. EA refers to activation energy, R is gas constant, and T is the temperature, right? Okay. Now, what is this e to the power minus EA by RT? E to the power minus EA by RT is the fraction of molecules having energy barrier more than that of activation energy. Therefore, K is a rate constant. It varies with temperature. As temperature is varied, this value increases. Therefore, K value increases. A is a frequency factor constant for a particular reaction. For different reactions, A value is different. Okay. Now, by taking the log value will be useful. So, taking the log to the base E, K is equal to log of A into log of, this is into is there, therefore what we can do, plus log of E to the power minus EA by RT. All these are to the power E, to the base E. By taking logarithmic expression will be of more use. Now log of K to the base E is equal to log of A to the base E plus minus EA by RT. Why it is so? Minus EA by RT. It is because log of A to the power M is equal to log M log A, M log A, or M to the power N. Log of M to the power N is N log of M. So log of E to the base E. These are all derived, but the important to recall oftenly is equal to log of A to the base E plus or minus, this is minus, okay, minus, plus into minus is minus EA by RT, and log E to the base E is 1. So this is again a useful expression. Okay. Suppose if you want to draw a graph where y-axis is log of K to the base E, log of K to the base E, and this is 1 by T, say. How could be the graph? So you can assess it by taking y is equal to mx plus c form. It is also in that form. This is drawn in y-axis, 1 by T drawn in x-axis. Therefore, what is left out is the m value, slope value. So since it is having negative sign, the graph should be like this. Okay, so many such kind of curves are there, and try to relate this with the expressions y is equal to mx plus b. Very important way that you can remember or correlate and remember. Now, what is this? This is nothing but log e of log a to the base e. This is intercept c value, and the slope, by the slope you can able to calculate ea value, because slope is equal to minus ea by r, minus ea by r. To make it more useful, logarithmic base 10, k to the base 10, if you do logarithmic k base 10, you have to multiply it by 2.303. 2.303. Okay, here also you have to multiply by 2.303. Okay, or the 2.303, and here this expression is not having 2.303, and you can divide everything by 2.303. Therefore, this will be the expression. If you want this in logarithm 10, this is the expression that we are using, right? So these are, again, this is another expressions that we use it. Yes. Now, here I have written e to the power minus ea by rt. How do you find out this value? How do you find out the fraction e to the power minus ea by rt? Okay, so let us take x is equal to e to the power minus ea by rt, right? If you want to find out fraction of molecules having more energy than activation energy, take the logarithm of x. Log of x to the base e, you take this. Log of e to the base minus e to the power minus ea by rt to the base e. Or you will get log of x to the base e is equal to minus ea by rt log of e to the base e, that is equal to 1. You can find out log of x value just by dividing ea by rt with a negative sign. Then find out the anti-logarithmic value to get the value of x. This is the way we can able to get the fraction of molecules having energy more than the activation energy, right? So these are the important areas to be, okay? Right. All graphical representations are to be related with expressions, numerical expressions, so that you can easily remember. Right. Now, how do you draw? If you want to draw, I would like to suggest how you can apply that, right? Suppose if you want to draw the graph of T half versus R naught. T half versus R naught. If the graph is something about that, when half-life period is drawn versus initial concentration, how could be the graph for the zero order reaction, and first order reaction, and write the slope of 8? Maybe asked like that. Then how will you write? So this is T half versus R naught. So try to find the numerical relationship between that. Okay, expression of this T half is equal to R naught by 2K, right? Suppose if R naught is here and T half is in the y-axis, then this is equal to y is equal to mx plus c form. This plus c is not there, then it is 0. Then it is to be considered as 0, right? R naught is x, therefore 1 by 2k is the slope, right? And this positive sign is there, therefore, and it should pass through origin. Okay. So this is the way we can able to draw the graph. Okay. And related graph related question will be there. Sure question will be there on that. Right. Suppose the same thing is to be done for the first order reaction. For the first order, if we have to draw T half versus R naught, initial concentration. So what is the expression that we have for first order reaction? T half is equal to 0.693 divided by K. There is no R naught at all. R naught is not there. That means it is a constant. So T half will be a constant, whatever may be the R value. Whatever may be the R naught value, T half will be a constant, whatever may be the R value. Therefore, it is nothing. Slope is 0. Right? So this is the way you can able to draw the graph clearly. Given question, recall the numerical expression behind it and then go ahead with it. Right. Now we quickly look into the questions, objective type questions which can be asked in this area. Right. Now, come on, are you ready? Whether you have joined? Okay. Instantaneous rate of a chemical reaction is rate of the reaction in the beginning, rate of the reaction at the end, rate of the reaction at the given instant, rate of the reaction between two specific time intervals.
Option C.
So, option
C.
Option C, right. It is the instantaneous rate is the rate at a given instant, given moment, denoted as d by dt, right? Change of concentration versus time, instantaneous rate, right? Okay, you are right. So this is the rate of reaction at a given instant. For 3A giving rise to 2B, the rate of dB by dt is equal to rate of dB by dt equal to, you need a pen and paper. You can try, take some time, and then you can do.
C, sir.
You are asked to find out the value.
C, sir.
Okay, dB by dt. You are asked to find out the value of dB by dt. Okay. And these are the answer. In terms of
C, sir.
C? Okay, are you sure? C is not the right answer. Want to change the answer?
B, sir.
C.
B, sir.
Okay, can you put the messages also? Messages I can read. I have made the arrangement here. Okay.
Option B, sir.
Option B, right. So why it is option B? Just think about it. This is reactant. So what you have to do is the stoichiometric is to be divided and d of A by dt. This is the expression for rate. Rate is equal to, in terms of concentration of a reactant, it is 1 by 3 minus 1 by 3 dA by dt. This is equal to 1 by 2 dB by dt, right? dB by dt. This is the definition. If a equation is being given, this is the definition when stoichiometric coefficients are to be divided. This is what we have told morning. Yes, right. Now only this is asked. Come on. Am I blocking? Not so, no? Okay. So dB by dt is asked. This 2 is to be transferred here, right? This 2 is to be transferred here. Therefore, minus sign is to be retained. Therefore, it is B value. Okay, fine. Okay, come on. Yeah. Units of rate constant of first and zero order reactions in terms of molarity M. Units are respectively.
Yes. Option C. C, sir.
And zero order. You have to take first.
Yes, sir.
A.
A, sir.
Any other answer?
Yes, sir.
A, sir.
Okay. Right. For first order reaction, it is per second. And for the zero order reaction, it is moles per liter per second. Moles per, okay, moles per liter per second. Okay. This is the constant, this is a unit of rate itself. Right. So moles per liter is capital M per second. Right. A is the correct answer. Which one of the following statements for the order of a reaction is incorrect? Order can be determined only experimentally. Order is not influenced by stoichiometric coefficients of the reactants. Order of the reaction is sum of the powers to the concentration terms of the reactants to express
Option
the
D,
rate
sir.
of the reaction.
D,
Order
sir.
of the reaction is always a
Option
whole
D,
D,
number.
sir.
Option D, sir.
Option is D.
Option
Okay,
D,
it is-
sir.
Option
Okay.
D, sir.
Very good, very good. Option D, you are right. Order of a reaction cannot be always a whole number. It can be a fraction also. Fine. Good. A zero order reaction is one whose rate is independent of the concentration of the reactants, the temperature of the reaction,
Yes, sir.
concentration of the
Option A.
product, the material of the vessel in which the reaction
Option
is
A,
carried
sir.
out.
Option A, sir.
Option?
Option A, sir.
Yes, sir.
Okay, the zero order reaction is one, the whole rate is independent of the concentration of the reactants. Okay. Right. Then the plot of concentration of reactant versus time for a reaction is a straight line with a negative slope. The reaction follows the rate equation of zero order, first order, second order, third
First
order.
order
Option
reaction.
B, sir.
Option B.
Option B,
Option
sir.
B,
B.
sir.
Think about it once again. The plot of concentration of the reactant versus time. B is not the right answer. Okay.
Option A, sir.
Concentration of A or R versus time is like this. For the general reactions, any general reactions,
Option A, sir.
concentration of R versus T is a thing like this. That is, for the first order reaction, log of R versus time is a straight line.
Option C, sir.
Option
C.
C. For a zero order reaction, this is for a zero order reaction, concentration of R versus T is a straight line. Concentration of R versus T for any other ordered reaction, it is a curve. R versus T, it is for zero order, right? Zero order reaction. Okay. So we have taken that log of R versus T. This is the integrated rate expression. Log of R by D. If it is given as log of concentration of the reactant versus time, then you have to choose first order. So it is the zero order reaction. Remember, it is a zero order reaction. A reaction proceeds by first order. 75% of this reaction was completed in 32 minutes. The time required for 50% completion is?
Option B, sir.
Is it so?
Option B, sir.
Okay. So this is the start of reaction. This is half of the reaction, say. This is T half. Okay. So now 75% is over. This is 75%. This is 50%.
Option B, sir.
Say this is 75%. So total time here taken is 32 minutes. Right. So you are asked to find out the time taken for 50%. Confusing?
Option B, sir.
Option B is the right answer. Option B is the right answer. So it is something maybe confusing for others. See, the time required for 50% of this. See, this 50% is 16 minutes required. And for this to become half, 50 to become half means 75. Right? 50 to become half of it, its value. So 75, up to that, it needs 8 more minutes, half of this. Sorry, the 16 minutes again. It needs 16 minutes. Okay. So 16 plus 16 is 32 minutes. Therefore, 16 is the right answer. Now, again, this is 25. Half of it. Half of it means 12 and a half. 75 plus 12 and a half. So that is 87 and a half. For 87 and a half%, again, time required here to here is 16 minutes. Okay, this is what the logic of first order reaction, and this is how the radioactive disintegration is a first order kinetics, and disintegration occurs in this way. Okay, this is 16 minute, right? 16 minute. Activation energy of a chemical reaction can be determined by evaluating rate constant at a standard temperature, evaluating velocities of reactions at two different temperatures, evaluating rate constants at two different temperatures,
Option
changing
A, sir.
concentration of reactants.
Option C, sir.
Option C. Okay. So, activation energy of the chemical reaction. Activation energy, how it is related is log of K2 by K1. The last expression which is used there, K2 by K1 is equal to EA by 2.303 1 by T1 minus 1 by T2. Okay, 1 minus 1 by T2. Okay, I will write here 1 by T1 minus 1 by T2. Right? This is into. Okay. Now, log of K2 by K1 by measuring the velocities or the rate constants, velocities at two different temperatures, we can able to calculate EA from this expression. Right? Log of K2 by K1. Right? So, evaluating velocities of the reactions at two different temperatures, evaluating rate constant at two different temperatures, evaluating rate constants at different temperatures, right? This is the thing. It is, I mean. Okay. Changing the concentration of reactants, by changing the concentration of the reactant, we determine the value of alpha and beta, the powers of the concentration term in the rate law expression. Okay. Therefore, these wordings are being given. So what I want to tell you is, so this rate is equal to K into A to the power 2 and B to the power 3. If it is there like this, say, by varying the concentration of A and B, we calculate these powers. This is, if it is alpha and beta, this is determined by varying the concentration of, changing the concentration of reactants. We will find out that. Okay. Fine. Rate constant for a reaction is 3 into 10 to the power 3 liter moles per
Second order,
moles
sir.
per second.
Option C.
What of the reaction will be?
Option C.
Option C. Good. Which JNV?
Bangalore Urban, sir.
JNV?
Bangalore Urban.
Bangalore Urban. Fine. Anybody else? How he has calculated? Is he having computer or he is having calculator with him? Nothing. It's of no use at all. This here, this is the indication. What is the unit of rate constant for the second order reaction? It is liter per mole per second. Rate constant, its units are different, right? For zero order, it is moles per liter. Okay, moles per liter per second. For first order, it is per second. For second order, it is liter per mole per second. So he observed only this to tell the answer, right? Now, rate law for the reaction between the substances A and B is given by rate is equal to k raised to k into a to the power n and b to the power m. On doubling the concentration of the A and having, making it half the concentration of the B, the ratio of the new rate of the earlier rate of the reaction will be.
Option C, sir.
Option C.
Yes, sir.
Option C, sir.
Very good.
Yes.
Yes. Somebody acknowledged as yes, correct?
Option C, sir.
Option C, right. So need a little bit of this. In the first extent, rate is equal to k to the power a raised to n and b to the power m. In the second rate 2. Rate 2 is k a to the power 2a. It is doubled. 2a to the power n and b is 2b. 2b to the power m. Because on doubling and making it half. This is not 2, this is half. Right. Except 2, this is all. Okay. So this is half of b to the power m. The rate 2 is done by this way. And this is k a to the power n, keep it as it is, and b to the power m, keep it as it is, 2 to the power n, and 1 by 2, that is nothing but 2 to the power minus 1. 2 to the power minus 1. 1 by 2 is 2 to the power minus 1 to the power m. Okay. Now this is rate 2. Rate 1 is this one only. Divide rate 2 by rate 1. So these things get cancelled. Okay. So what is remaining is 2 to the power n, 2 to the power n, and minus 1 in term is minus m. So this will remain. Right. So this is the answer. Therefore, it is the answer. The rate constant for a first order reaction is 6.9 into 10 to the power 3 per second. How much time will it take to reduce the initial concentration to its 1/8 value? It is a little calculation is involved. Try this. Take your pen and paper, write the expressions, substitute. Nearest answer you can say. So you are asked to find out the t value, how much time it will take. Okay. So 2.303, right, by k log of, it will take to reduce initial concentration. Initial concentration, if you take it as 1, the final concentration is 1/8 of its value. If this is x, this is 1/8 of the x. Okay. So this is a 2-mark question like, but it is asked here. 2.303 by k. K is 6.9 into 10 to the power 3. Log of 8, this will be log 1 by 8 is log of 8. Log of 8 is 3 log of 2. Okay, because look at this. Log of 8 can be written as log 2 to the power 3. So this is nothing but 3 log of 2. 3 into log of 2. 3 into log
Option
2
C,
is
sir.
0.3010. I asked you to remember this. Okay,
Option
for
C,
such
sir.
reactions it will be. So this will be 2.303 into 3 into 0.301 whole divided by 6.9 into 10 to the power 3.
3, sir.
Yes. See,
Yes, sir.
Yeah, C is the right answer. 2.303 into 3 point, this is 0.693. This, if you multiply these two, it will be 0.69693 into 3 divided by 6.9 into 10 to the power 3. Okay. So this ones are, this tens are. Right. If it is minus 3, is it minus 3? It should be minus 3. Then only we'll
Yes,
get the
sir.
value.
Yes, sir. -3, sir.
Yeah, it should be minus 3. It should be minus 3. Okay. And if it is minus 3, then we'll get the value 10 to the power minus, it becomes 10 to the power minus 2. If it goes up, it will be 10 to the power plus 2. 3 into 10 to the power plus 2 is 300. Right. This is the way we have to do. Therefore, 300 seconds we have got. Okay. In a reaction A plus B giving rise to products, keeping A as constant, if B is doubled, the rate becomes double. Keeping B constant, if A is doubled, rate becomes 4 times. The
Option C, sir.
overall order of the reaction is?
Option C.
Option C. Let others try. So what you have to do, you have to make use of this expression. Rate is equal to K into concentration of A to the power alpha, concentration of B to the power beta. Okay. Now, keeping A as constant, if B is doubled. Keeping A as constant, if B is doubled. Okay. B is doubled. Okay. 2 to the power beta. 2B is doubled. The rate also becomes 2. This is a simple equations that you should get. If B is doubled, only 2 you take. 2B. Instead of 2B, you take only 2. 2 to the power beta is equal to 2. That means beta is 1. Okay. If keeping B constant, if A is doubled, that means 2A. 2 to the power alpha. 2 to the power alpha. If A is doubled, 2 to the power alpha, it becomes 4 times. It becomes 4 times, means it is 2 square times. 4 times means it is 2 square times. Therefore, alpha is equal to 2. So overall rate of the reaction is alpha plus beta. Alpha plus beta is the overall order of the reaction. Therefore, it must be 3. Hope it is understood. It is an important question. So maybe asked for the 2 mark also, or in this way. The plot of concentration of the reactant versus time for a reaction is a straight line. It's a straight line with a negative slope.
Option A, sir. Zero order.
The reaction follows the rate equation. Okay, I
Zero
think it is
order.
already being taken, right?
Option A, sir.
Okay, fine. You are already it was done. Again, it has come, right? Okay. Now here it is a tricky question. So there is a table. Okay. So this is experiment number 1, 2, 3, 4. These are all the concentration of A. Concentration of A in A plus B giving rise to C.
Option A.
And concentration of B is given in this way. Initial rate is being given. Rate of the reactions when it is
Sir,
A is
option A.
taken as this and B is taken as this. The rate is this. Now, you have to give the rate expression.
Option
You
A,
have to give the
sir.
rate expression.
A.
Yeah. Whether you have done early only, how you can able to say so quickly?
Sir,
Can you
concentration
explain
of A is constant, no, sir. With the rate, and our concentration of B is power 3.
Okay, fine. You have correctly observed. Okay. For some, it is a 3-mark question. Elaborately, you have to find out alpha and beta for framing 4 equations. But for some for the one who can observe it very carefully, it is a very simple question, right? How it is so? What is to be observed? Okay. If you want to do it in a way that is required is, by experiment 1, we have rate is equal to concentration of A, that is 0.012 to the power alpha into 0.035 to the power beta k into a to the power alpha b to the power beta is nothing but rate. Rate is 0.1. In this way, we have to frame 4 equations. 0.024 to the power alpha, 0.0770 to the power beta is equal to 0.80. Then choosing the questions and dividing one by the other so that you will get the value of alpha and beta. This is the way that exercise books, exercise also such question is there. But in competitive examinations or objective type questions when it comes, what way that you can see here? Look at this. A is kept constant in experiment 1 and 4. By taking A as constant, by making A as a constant, if B is doubled, look at this, 0.035 to 0.7070, this is doubled. Keeping A constant, if B is doubled, what happened to the rate? It has become 8 times. It has become 8 times. That means concentration of B ranges cubically. Okay. If this is doubled, if it is doubled, it 8 times means 2 to the power R, 2 to the power beta is equal to 8. 2 to the power beta is equal to 8. That means 2 3s are 2 to the power beta is equal to 2 3s are 2 to the power 3. Beta is equal to 3. This is the way of analysis. Then coming to this. Now here these two are constant. Okay. A is kept constant, whereas B. Now we have to see where B is kept constant. Okay. When B is kept constant, 0.035035, B is kept constant. How A is varied? A is doubled, 0.012 to 0.024. If A is doubled, what has happened to the rate? It is remained same. Okay. Now what is the expression is, if this is keeping constant, if this is kept constant, if A is doubled, that means A to the power, okay, 2 to the power alpha. A is concentration of A to the power alpha was there. Therefore, 2 to the power alpha is equal to 1 because the no change at all, 1. Therefore, alpha is equal to 0. Alpha is equal to 0. So that this alpha has become 0. Now in the expression supposed to be k A to the power alpha B to the power beta. What we have to write? If alpha is 0 and beta is 3. If alpha is 0, it is not written here in the expression. Therefore, this is the answer. A is the answer. Okay. So other answers can be eliminated. Right. Okay. Now, in an exothermic reaction, delta H is the enthalpy. Then activation energy is more than delta H, less than delta H, equal to delta H, or cannot be predicted.
Option B, sir.
Less than delta.
Okay, this is EA. We usually write like this. And what is delta H? This is delta H. This is the energy of the reactant
less
and
than
energy
delta
of the
H.
product. This difference is enthalpy. And this is activation energy. So this is exothermic process, means the product is having energy less. What we can say?
So less than delta H.
Less than delta H. We cannot predict because these two are different things. Okay, this may be equal. There is no relationship given between these two, EA and delta H. Therefore, we cannot predict just by the graph, but just by statement we cannot able to predict. It may be more or less or equal, right? Delta H and this may be equal.
So if it is more, we have to supply energy, no sir?
Okay. If it
Then
is more,
we have to supply energy.
that doesn't matter, because whatever may be the energy here, this energy, threshold energy, is different for the reaction, right? This energy is different for the reaction. Okay, whatever that we have invested, we have to cross over this energy, then only result will occur. So it will be our energy plus whatever that we have invested. Again, that much energy may be given out. That is different. Okay, so it cannot be predicted by the graph or given information. Catalyst increases the rate of reaction by
Decreasing activation energy.
increasing
Option C.
enthalpy, decreasing internal energy, decreasing activation energy, increasing activation energy.
Option C, sir.
Option C. Option C, as it was shown there. This is the graph, and this is activation energy EA without catalyst. With the catalyst, the path is different. It fastens the reaction because EA is lessened. EA becomes less, decreasing activation energy. Come on, slope of the Arrhenius plot is equal to slope of the Arrhenius plot.
EA by R. Option B.
Option B.
Option A, sir. Yes, sir.
EA. Okay. Plot of this. Okay. The expression I will write here. Log of k to the base 10 is equal to log of a to the base 10 minus EA by 2.303 R T. This was the expression when we took the logarithmic expression. So this is plotted. Arrhenius plot means log of k to the base 10 or ln k, any one of this. Log of k to the base 10 versus 1 by t versus 1 by t. So it is having negative slope. It is like this. So this is the slope minus EA by 2.303 R. Minus 2.303 EA by R. That is the answer to this. So have the expression, clear expression, and then such questions can be addressed. In the first order reaction, A giving rise to B, if the K is rate constant and initial concentration of the reactant is A is 0.5 m, then half-life is
Option C. Option C, sir.
Okay. Initial concentration of the reactant A is
Option B,
0.5. Then half-life is, first order reaction half-life is 0.693 divided by K. Right? If K is the rate constant and initial concentration of the reactant A is 0.5, then half-life is, okay. So half-life is 0.693 divided by K. Okay. What is wrong there? If K is the rate constant and initial concentration of the reactant A is 0.5, initial concentration, half-life is, it doesn't depend upon this. Okay.
Sir,
So, yeah,
ln 2 value, sir.
it may be written in this way also. 2.303 log of 2 K. Okay. So 2.303 log is ln. Okay, ln2 by K. So ln2 by K, C is the option. And concentration has nothing to do with. This concentration has nothing to do with. T half is 0.693 by K. How 0.693 had come there? 2.303 into log of 2. Right? So 2.303, the logarithm expression is to the base 10. If you want to convert it into ln, that means log to the base E. That is log to the base E, log 2 to the base E and K. Therefore, this is the answer. Point the 5 has nothing to do with. Right. If X is the fraction of molecules having energy greater than EA, it will be given by
Option B, sir.
option B. Navodaya, mention your Navodaya.
JNV Kadapa, sir.
Kadapa, good. Very good. So this is the right answer. So X represents e to the power minus EA by RT. Right. So taking log of X or ln X, log to the base EX is ln X. This is equal to log of e to the power minus EA by RT. Right. So minus EA by RT, okay, log e to the base E, log e to the base E, this is equal to 1. So log of X to the base E is equal to minus EA by RT. Log of E is written as ln X is equal to minus E by RT is the right answer. Good. If the rate of the reaction is equal to the rate constant, the order of the reaction is?
You know.
Rate of the reaction is equal to rate constant. Then the order of the
Option
reaction
C,
is?
sir.
Option C?
Yes, sir. Option A.
Yeah.
Option A, sir.
Okay. See, the rate is equal to K into A to the power alpha. If the alpha is 0, it is a zero order reaction. If this is 0, then it is equal to K. Rate is equal to K if it is zero ordered reaction. Okay. So order of the reaction is 0. Okay. Chemical reactions with very high EA values are generally
Very slow, sir. Option A.
Very slow, sir.
option A. This is also
Option
option A.
A.
They are very slow. Fine. They are very slow. Okay. Now, the time taken for 90% of the first order reaction to complete is approximately 1.1 times of the half-life, 2.2 times of the half-life, 3.3 times of the half-life, 4.4 times of the half-life.
Option C, sir.
Option C. How you have done, man?
Sir, after 3 half-lives.
Okay, fine.
Option C, sir.
Option C. Okay, fine. The time taken for 90% of first order reaction. So this also you have to find the ratio. T90 is equal to 90%. Shall I, if I write like this, this is 2.303 by K log of, if initial concentration is 100, the 90% is completed means the final concentration is 10. Log of 100 by 10 is 10 itself. Okay. So that log of 10 is 1. Okay, this factor won't come. Log of T90 is 2.303 by K. T half is equal to, for the first order reaction, it is 693 divided by K. You take the ratio of this. Time taken for 95, T90 by T half. That is 2.303 by 693. If you do that calculation, you will get 3.3 times. Fine. This is the way you can do. Fine. The reaction involving two different reactants can never be unimolecular reaction, first order reaction, second order reaction, bimolecular reaction.
Option
Yes, sir. Yes, sir.
Option A. Option A. It cannot be a unimolecular reaction. Okay, fine. Okay. Okay, fine. This is what to be understood, right? From the point of view of from the point of view of chemical kinetics, right? So hope you will take up the challenging questions and practice the numerical expressions, because these are all numerical based chapters and more and more questions are to be solved. Okay. So we'll take up the electrochemistry. We'll take up electrochemistry and some basic concepts of electrochemistry. I will tell you, and tomorrow we'll do the objective type questions based on that. Okay. So this is electrochemistry, right? So what is electrochemistry? Electrochemistry is a study regarding the energy changes of what? Changes of electrical energy into chemical energy, or chemical energy into electrical energy. So electric chemistry is something about this interconversions, you can say, right? So we used to have battery cells, okay, pentorch cells. All these are giving electrical energy at the cost of chemical energy, right? So we have got the battery cell, car batteries, which is called lead cell. So it also, at the cost of some chemical, it is giving electrical energy, right? So some cells are rechargeable and some cells are use and throw type. That means the chemicals which are used up in the reaction. So electrochemistry, basically the application or the use of redox reactions. What are redox reactions? Redox reactions are those in which oxidation and reduction takes place, right? And let us take an example. If a zinc rod is dipped in copper sulfate solution, suppose if this is a situation, what do you observe? Is it a redox reaction observed? So you find that this zinc rod dipped in copper sulfate solution, this zinc gets less and less. Zinc metal becomes less and less. It will form its ion, or zinc present there will form zinc ions. That means this is possible by losing 2 electrons. Zinc metal will react with copper ion, and the blue color of the copper sulfate fades after some time. It fades, right? It becomes colorless when completely it gets reacted, right? Because zinc rod is being dipped, right? So if the copper sulfate containing copper ions undergo reduction, that means that taking 2 electrons become copper. So the overall reaction is zinc turning itself into zinc 2 plus ion, and copper 2 plus ion is converting into copper. Reduction as copper has been seen. This is what the redox reaction that we observe when directly a metal is dipped into the aqueous solution of another metal. So here zinc is considered to be more reactive than copper metal. Therefore, it can displace copper ion from the salt solution. Suppose if it is done indirectly. Indirectly means what? The arrangement is little different. If zinc is dipped in zinc sulfate solution, its own ionic solution, copper is dipped in its copper ionic solution, both are separated by a salt bridge, okay? And if these two are connected with the external wire, this is externally if they are connected, then what we find is current flows. When the circuit is closed, this current starts flowing. This is what we are going to observe, right? So there is a need of salt bridge. Or the self electromotive force, or EMF for short. Okay. This zinc here, what we find is zinc is undergoing again the same way corrosion. That means zinc starts forming zinc 2 plus ion. Okay, and sends its 2 electron to the copper. And the copper ion present here in the solution again gets deposited over there. Copper ion deposits there by taking this electron. That means copper 2 plus ion takes this 2 electron to form copper. The same reaction as we have observed in the first case, when the direct redox reaction has taken place, we are doing it indirectly, means the same reaction is occurring, right? So by this, what happens is zinc 2 plus ion concentration increases here, and the copper 2 plus ion concentration decreases. So there is a chance that this solution becomes ionic or having charges. So to neutralize that, there is salt bridge. So the purpose of salt bridge is to give the counter ions so that to neutralize the half cells. Each one is called half cell. When a metal is dipped in its own ionic solution, it is called half cell. Now, by the time when zinc 2 plus ion is formed, the salt bridge containing potassium ion, 2 of the potassium ion it releases. Sorry, 2 of the nitrate ion it releases. Nitrate ion. So zinc 2 plus ion and 2 nitrate ion, NO3 minus 1. 2 charges, 2 negative charges are required, therefore 2 NO3. So it neutralizes. So the solution won't become charged. Similarly, when the copper 2 plus ion is deposited, the sulfate ion will become rich. It will be negatively charged. Therefore, the K plus ion is being released through the salt bridge. Salt bridge consisting of neutral salts like KNO3, KCl. When AgNO3 is not used, we use KCl. And this is a kind of a tube which contains agar-agar. So agar-agar powder which is heated, which becomes porous, and it can hold the solution. It can hold the solution. It is simply an arrangement to supply the neutral, to maintain neutral electrical neutrality and to complete the circuit. These are the 2 purposes of salt bridge. And voltage, you can find voltmeter, the readings also. Okay. So when this is connected, we find that 1.1 volt, 1.10 volt in this voltmeter. Okay. The quantity of voltage can be measured through this. So this is what happens when it is indirectly done. And this is called electrochemical cell or galvanic cell. Galvanic cell, right? So an electrochemical cell or the galvanic cell is one in which chemical energy is converted into electrical energy. Okay, chemical energy is converted into electrical energy. Okay. Okay. Now, so what is electrochemical cell? It is a device which produces electrical current by means of spontaneous redox reaction. Spontaneous redox reaction, this happens. So each half cell is we can call it as half cell. It is also called galvanic cell or voltaic cell, and it consisting of 2 half cells with 1 electrode each. Okay. Now oxidation takes place at anode. One in which oxidation takes place is anode, and one which reduction takes place is cathode, right? So there is oxidation half cell and reduction half cell. We can construct many number of electrochemical cells by making this redox couple. The metal in its own ionic solution, okay, it's a redox couple. By taking many such redox couple, many electrochemical cells can be, or galvanic cells can be constructed, right? Okay, right. Now, the construction of simple voltaic cell needs 2 half cells. That's the only thing we can able to do with many number of the metals that is available, metal and its ionic solution available. Now, what is meant by electrode potential? The electrode potential is a tendency to lose electron or gain electron when the metal is dipped in its own ionic solution. It may have the two kind of tendencies. The metal may lose its electron and form an ion, or ionic species which is present in the solution may get reduced to metal itself. So both tendencies. So the tendencies is called electrode potential. So we say the standard electrode potential when the concentration of all the species involved in the half cell is unity. If the concentration is unity, then it is called standard electrode potential. So we are represented by E naught standard, right? So zinc copper cell, let us know more about the zinc copper cell, right? Cell components for zinc copper cell are, okay, so zinc dipped in zinc salt solution, copper dipped in copper salt solution, and they are connected, and we find that this will give 1.1 volt. As I told you, it will give 1.1 volt, right? So this is the arrangement. Zinc, copper, and KCl is being used there. 1.1 volt we have got, and there is each electrode, there will be reactions. Zinc is zinc atom converted into ions, okay, and there is a deposit of copper ion from copper sulfate. This is what being seen, okay. Now, if copper silver cell, what is meant by copper silver cell? Copper is dipped in its own ionic solution, copper sulfate, and silver in silver nitrate, right? So we find the voltage is different for this half cell. This difference, it is because of relative tendencies or electrode potential values, okay. Now this is a copper silver cell. Copper strip is there here, copper dipped in its own solution, silver in silver nitrate, right? And we got 4.462. Now, how this can be measured then? How electrode potentials can be measured? For measuring electrode potential, there must be one half cell of which we assume standard electrode potential of that half cell is 0. That is standard hydrogen electrode. Standard electrode potential is measured by using standard hydrogen electrode. Standard hydrogen electrode it is assigned an arbitrary voltage of 0, right? So this is how the standard hydrogen electrode is. It consisting of a platinum metal, inert metal, which is dipped in 1m HCl, and the hydrogen gas is bubbled through it. That means platinum metal is in touch with two species. One is H2 gas, another is H plus ion. H plus ion is present in HCl. Suppose from the other electrode, when it is collected, other electrode gives an electron. If other half cell gives an electron, this H plus takes the electron and forms H2 gas. So two such H plus ions takes 2 electrons, will form H2 gas. So the H plus ion concentration here in the HCl reduces, right? And it will give hydrogen gas, more and more hydrogen gas. When suppose if the copper half cell is being connected, the copper is less reactive than hydrogen, then this means it will give electron. So it has to undergo, hydrogen gas has to undergo oxidation. So it will undergo oxidation. Therefore, it produces 2H plus ion and 2 electrons. So hydrogen gas at the where platinum is there, it will send the electron through it, forming the concentration, more and more concentrated acid you are going to get, right? So standard hydrogen electrode whose voltage is considered to be 0 may undergo oxidation or it may undergo reduction depending upon what the other half cell is. If standard hydrogen electrode is connected to zinc half cell, Zinc dipped in its own ionic solution, zinc half cell. Zinc is relatively more reactive, therefore it sends an electron. It has to take the electron and undergo reduction. This is the half cell, which is the half cell reaction formed when it is connected to zinc half cell. So this is what we have to understand. Okay, when zinc and standard hydrogen electrode, this is being taken, zinc and standard hydrogen half cell, if it is taken, then so this is being connected, we get 0.76. So this potential is considered to be 0, therefore this is the measure of electrode potential value. Always we express potential as reduction potential, and since oxidation is going on, this is a better metal and oxidation is going on here, its electrode potential value, that is E0 value of zinc 2 plus bar zinc, okay, this is reduction, this is taken as minus 0.76. Why this minus sign? Because we want to know the reduction tendency of each species. We always compare that. Reduction potential, we always customarily we are striking reduction potential. Voltmeter doesn't give this with this sign, right? So the sign is being given minus because it is undergoing oxidation. It is undergoing oxidation. So if you want oxidation potential is, you have to reverse the sign. E0 oxidation potential, that is E0. So zinc bar zinc 2 plus is 0.76. 0.76. This is the way that we can write. So for every species, we write reduction potential. If you want to, the other one, you can change as the sign and you can take oxidation potential is plus 0.76 and so on. Now, when the copper half cell is connected to standard hydrogen electrode, okay, standard hydrogen electrode, copper half cell is connected. So it is all standard conditions are maintained, say 1 m copper sulfate solution, 298 Kelvin, all this. When it is connected to this standard hydrogen electrode, we get 0.337. This is plus because reduction is going on here. Reduction is going on. Reduction potential is 0.337. So E0 of Cu2 plus / Cu is 0.337 or 34. You can say 34. Okay. Now, when this half cell, okay, what I want to tell is when E0 of zinc 2 plus bar zinc is minus 0.76. When these two are connected, we are getting E0 of the cell. Okay, E0 of the cell is E0 right minus E0 left. E0 right is 0.34. E0 right is where the reduction takes place, minus E0 left, that is minus 0.76. Therefore, this is 1.10. So why we are observing 1.10 when the zinc half cell and the copper half cells are connected? Because each half cell has got standard electrode potential, right? Okay, there is a table of electrode potential which is being given in your textbook also. You might have seen this. So it is in the decreasing order of electrode potential values of the different species. Fluorine undergoing reduction to give fluoride ion, F minus ion, is highest, 2.87 among that. Okay. So one which is very down is lithium ion undergoing reduction is minus 3.4. Minus 3.04. And also species are being given. Hydrogen is considered as 0. Hydrogen is considered as 0. It is there in the middle. Okay. So one which takes the electron easily makes the other species to lose its electron. Therefore, it is an oxidizing agent. It is undergoing reduction fast. So it is a stronger oxidizing agent. So lithium metal, okay, this tells that lithium metal can do lithium ion very quickly. Therefore, Lithium is a strong reducing agent. This is a strong reducing agent. Lithium is strong reducing agent, this metal. So this is what we learn from these electrode potential values, and this is called electrochemical series. Arrangement of species in the decreasing order of their electrode potential is called electrochemical series. Now what we have observed is fluorine is having highest. Okay, for the metals, for the strong metals, it is negative. Why it is negative? Because they readily undergo oxidation, therefore reduction potential is negative. Okay, whenever Mg2 plus 2 electrons giving rise to is negative, this is not going to occur in this way, but reverse way. It usually it occurs in this way. Mg giving rise to Mg2 plus 2 electron. This tendency is positive, 2.36. What is positive, that is what will be undergoing in the chemical reactions. Magnesium loses its electron. Okay, therefore it is positive. Now compare that magnesium and sodium. Okay, compare this electrode potential, and can you tell me which is more reactive species among these two? In order to compare the reactivity order of magnesium and sodium, take these two equations. Sodium forms sodium ion plus 1 electron. That means it is the reverse process. So it is this process is having minus 2.71, and the opposite process is 2.71. Now compare this mathematically. This is greater than this value. Therefore, this is likely to occur more easily than that. So sodium is a better metal, strong metal. It can undergo oxidation more readily than magnesium. This is what we have to imply. By using electrode potential value, when we have to compare the reactivity of the metals, then compare the oxidation potentials. Because metals undergo oxidation, compare the oxidation potentials. Thereby you can able to write which metal is more stronger. Okay, so remember that electrode potential value is an intensive property. What do you mean by this? Intensive properties doesn't depend upon the quantity of the substance. If you have taken a big electrode and don't think that it has the more tendency to give the electron, it is not so. It doesn't depend upon the quantity. Okay, so standard electrode potential, suppose zinc gaining 2 electrons, zinc E0 reduction is minus 0.76, and so if doubled, this quantity is doubled, say, so E0 of the reduction potential value won't increase, the same thing, it remains same. Therefore, it is an intensive property. E0 is an intensive property. So this is what I have told you, that what is the electrode potential, use of electrode potential. So we can find out which metal is more stronger, which metal is less stronger, and all this. Okay. Now for such questions you can able to solve. Will silver ions, Ag plus ion, oxidize metallic nickel to Ni2 plus? Silver ion, whether it can change Ni2 plus ion into metallic nickel to Ni2 plus, whether it changes Ni to Ni2 plus. Okay, if this is what you want to see. So arbitrarily you can frame an equation and you can able to find. Let me tell you how it is so. This is the application of electrode potential values. Consider the displacement of silver. So nickel is there, Ag plus ion, whether it can be able to make nickel into nickel 2 plus ion. So that Ag plus ion should be Ag. So arbitrarily we take this as a electrochemical cell. Okay, in which nickel half cell, Ni to Ni2 plus is oxidation half cell, left half cell, and Ag plus Ag, silver nitrate in silver metal in the silver nitrate is another half cell. Okay, so we want to test whether this reaction is occurring. For that, we calculate the E0 value. E0 value is E0 right reduction minus E0, okay, reduction potential of anodic half cell, cathodic half cell minus anodic half cell. So these values are known from the table. 0.80 minus 0.28. this is positive. E0 value is positive. If E0 value is positive, that means this reaction is spontaneous. This reaction occurs. So to test the spontaneity of the reaction, arbitrarily construct an electrochemical cell and predict the E0 value. If the E0 value is positive, then the reaction is going to occur. If E0 value is coming to be negative, then that reaction won't occur in that way. Okay, so this is what we have learned from electrochemical, from the reduction potential values. Increasing strength of oxidizing agent is to be understood like this. This is the increasing strength of reducing agent. So lithium is strongest reducing agent. That point I have told you. So for this also, this is the needed. Now check your understanding. Which of the following statement is not correct about inert electrode in a cell? Inert electrode. It does not participate in a cell reaction. It provides surface either for oxidation or for reduction reaction. It provides surface for conduction of electrons. It provides surface for redox reaction. It provides surface for a redox reaction. Both won't occur at the same place in an electrochemical cell, right? Therefore, 4 is not the correct thing. It is a not correct, okay? So that is what being asked, right? Now depict the galvanic cell in which the cell reaction takes place. Depict the galvanic cell. So which is the half cell, it is the left half, right half, you have to say. Okay, so this is the cell representation. Cu/Cu2 plus. Cu is undergoing oxidation. Oxidation half cell always to be written at the left side. Double slash indicates salt bridge. Ag plus to Ag. This is the way we write. This is left half cell. This is right half cell. Okay. So there is an abbreviation that you can make use of to remember. LONE. Left half cell. L stands for left. Left half cell in which oxidation takes place. Right. This is anode. This is called anode because it is electron rich. Because it is giving electrons. Undergoing oxidation means it is giving electron. And this is negatively charged. Negatively charged one, it is negative. The sign assigned to this is negative. So anode is negative. LONE will make you to remember the characteristic of the anodic half cell or the left half cell. So this is the way of representation of an electrochemical cell. So if it is a standard electrochemical cell, then this should be 1 m and the concentration of this should be 1 m. And the temperature is 298 Kelvin. Okay. So we mention the concentration also whenever it is to be written. Okay. So depict the galvanic cell in which the following reaction takes place. Zinc plus 2 Ag plus aqueous giving rise to zinc 2 plus. Okay. This is all to the power. Okay. Zinc 2 plus and 2 Ag. Also indicate in the cell which electrode is negatively charged. Okay, we'll try this here only. Depict the galvanic cell in which the following reaction takes place. The galvanic cell, which is the left half cell. The one which is undergoing oxidation. So this is zinc/zinc 2 plus, right? Sometimes this also can be written solid. This is aqueous. Double slash. Silver ion. Ag plus. Aqueous. Bar Ag solid. This is the way of representation. Which electrode is negatively charged? Which electrode is negatively charged? Remember that. Which is negatively charged? The left half cell is negatively charged. Zinc bar zinc 2 plus electrode. Zinc/zinc 2 plus electrode is negatively charged. This is the way of saying that. What are the carriers of current in the cell? What are the carriers of current in the cell? Okay, carriers of current. So externally electricity moves, so electrons. What is the individual reaction at each electrode? Individual reaction at each electrode is zinc giving rise to zinc 2 plus ion plus 2 electron. This is the half reaction. Ag plus giving rise to Ag plus electrons. Okay, this is the another half individual cell reaction. Okay, this is the way that you have to write. Okay, so these are the important aspects of electrochemical cell. So electrochemical cell is not yet over. It is we have to deal with the Nernst equation and some relationships between delta G thermodynamic factors and electrolytical cell, conductivity cell, and some other day-to-day life, that the cells that we use in day-to-day life, the chemical reaction involved in this, all these things will deal in the evening electrochemical cell, right? Any other doubt or any other thing that you would like to say, you can ask me. Otherwise, we'll wind up. Okay. Right. Thank you. We'll end the stream.